Okay, hello. In this video, we're going to discuss a big idea for strength of materials. And this idea transcends lots of branches of engineering and science. The idea is scaling. What happens if you make something bigger? And I mean bigger in all dimensions. Like suppose we start with the house. So I've got some house structure here. And suppose I want to make a bigger house, so I make everything bigger. I make it twice as tall, but I don't just make it twice as tall. I take all the beams that I used to build the house, so I take this thin beam here, and I make it twice as wide. And I also make it twice as thick this way. So everything that I use for the house gets twice as big. So the question is, if I make everything twice as big, will the house be equally strong? In other words, will the house still stand up just as well? And the answer to this question is no. All right, let's try to see why it doesn't work. Well, I'm going to compare two beams. One which is twice as big in all dimensions as the other. And in both cases, let's try to find the stress acting on the bottom surface. Okay, so we know stress is force divided by area. What's the area of this bottom surface? Well, it's W times W. What's the weight pushing down? Well, that would be the volume, W times H, times the density, times little g. So volume times density gives you the mass, mass times g gives you the weight. Okay, now let's have a look at the supersized beam over here. That's going to be the area over which it's acting would be 2w times 2w, and the weight would be the volume, 2w times 2w, times the height, which is 2 times h, times the density times little g. Okay, and let's see, on the left, the w's cancel, and we're left with h dg, and on the right, the 2w cancels with the 2w's, and we're left with 2hdg. So as I supersized this beam, the stress did not change the same. Did not stay the same. And stress is such that if it exceeds a certain point, the material will no longer be able to handle that stress. Once you exceed the ultimate stress of that material, the material will break. So what we're seeing here is that as you make things bigger, even if you make them bigger in all dimensions, the stress will go up, causing the object to fail. Okay, so suppose you're, just as an application, suppose you're watching a movie and there's like some spider in the movie. Is big. So there's some people in the movie, and those people are trying to run away from this huge spider, okay? So like, running away from the spider. Okay, let's see, from a scaling perspective, should the people run away? So there's this huge spider the size of a car sitting over there. It's like, looks like the same shape and size as a normal spider. Well, the thing is, if it's the same shape and size as a normal spider, then the stress on its legs are going to be not the same as a normal spider. So the spider has gotten many times bigger. So the stress on the legs of the spider is going to go up. So even though the spider's legs are getting proportionally thicker, just like we had in the previous example with the two posts, even though the post is getting thicker, the stress in each one is going to get higher and higher. So unfortunately for the spider with those thin little legs, the spider will not be able to stand up. The legs would just break. So for a big spider, those small legs would not work. So this person actually doesn't really need to run away. It just needs to get out of reach of the spider. The spider wouldn't be able to go anywhere. If you actually tried to supersize a spider, what would it look like? Well, you'd have to make the legs thicker. So if you tried to supersize the spider, you'd have to get these really thick legs drawn here. I got some thick legs. So what would it look like? Well, you'd have some body. Here's the body of the spider. And the spider would kind of take this shape. Of course, I'm kidding with you a little bit. This is obviously a picture of an elephant, but you can see the elephant has to have those really, really thick legs. It can't have spindly little spider legs because it wouldn't be able to support itself. So that's a result of scaling. Finally, just a couple other comments to connect scaling in this class to some other things. Like suppose you've got a star and you make that star bigger and bigger and bigger and bigger. Does it just become a brighter and bigger star? The answer is no. After a certain size, that star becomes a black hole, and so its nature changes quite a bit. How about a meteorite? If a meteorite gets bigger and bigger and bigger, eventually has so much gravitational force that it will tend to force its shape to be a sphere. So a protrusion in one direction on that meteorite there'll be so much gravitational force pulling it towards the center, it will tend to basically get crushed and make it into a sphere. And we might then call it a moon or something else. How about a resistor? If you change the dimensions of a resistor, an electrical resistor, so if you make it twice as, maybe this half as long, half as wide, half as thick, what happens to the resistance? Does it stay the same? The answer is no. As you shrink that resistor, its resistance is going to change. So these are all examples of scaling, and kind of an important idea in engineering. So we did an example here with strength of materials. I'll